Good morning, everybody. Nice to see so many of you still turning up on a third day in. My name's Errol, and I'll be taking you through the next a couple of days. If you can see me and you can't hear me, let me know. Otherwise, we're going to kick straight into it. Does anybody have any questions about the last couple of days that you've been through with Hashan? Has anybody been through any of the tutorials and have any questions about the tutorials that they've done so far? No, okay, no worries. Well, if you don't have any questions for the moment, I'll ask everybody to just mute themselves and unmute yourself if you have any questions. So I do quite like the sessions to be as interactive as possible, because the more questions you guys ask, the more knowledge we all gain. So if you think of anything at any point, don't be shy, just shoot your hand up or chuck a message in the chat. Alrighty, I'll turn my camera off for now. So today we're going to be going into the solver. So we've done our meshing, we've done our geometry preparations, and today we're going to look into the solver, and we are going to get a little bit nitty-gritty into some of the numerics, but not too much. Sorry, question here. We can go through the basics of meshing when I set up my other model. We'll do a really quick run through. But yeah, so mostly into the solver and into some post-processing today. We're also going to look through a few more advanced models at certain points, and some definitely some more advanced models again tomorrow. Okay, but we'll go back through some of the introductory stuff in just what CFD is that I think you covered probably on your first day. So we're going to be looking at the whole point of this session is to understand Ansys CFD workflow and understand some of the best practices. And so what are we doing? Why do we do CFD? We want to solve physics equations to characterize fluid flow. Now it's very broad. There's a lot of different uses for CFD. You can see on the screen there, we're going through a front wing and a wheel. So it can be used for picking up pressures, forces, density, mass and momentum in a case for a aerodynamics vehicle, so a vehicle with aerodynamic surfaces. But there's a myriad different uses that we can use for CFD, things like multi-phase, where you can have fluids and gases in the same simulation. You can have discrete phase modeling, so that means we've got particles coming in, species, we've got different types of gases and interactions. We can also have some combustion in those species simulations, loads of different applications. So the purpose is to provide detailed information, so pressure, velocity, temperature, multiple phases, forces, lift and drag, species composition, and it's used throughout the engineering process. So conceptual studies of new designs, detailed product development, troubleshooting, optimization, and redesigns. We'll go through some of the applications in some examples as we go through as well. So how it works, you can see we basically need to break a larger domain up into discrete control volumes. So that's what we're doing when we're meshing. When we generate a mesh, we're cutting up our domain into these little control volumes for which we are calculating. We're calculating our mass conservation and momentum conservation. Okay, and the actual equations we're solving are called the Navier-Stokes equations. So, or RANS, so Reynolds averaged Navier-Stokes equations. These are really important equations. You don't have to know, you don't have to memorize them, you don't have to know exactly what they are or how to discretize them or turn them into algebraic solutions that we can solve numerically, but it is important to understand that what is going on in the background are these really powerful equations for fluid dynamics. And a really good way of understanding it is we need the two different sides to balance out. So you can see on the left, we've got our transient and our convective terms. They need to equal our diffusion and our generation terms. Okay, now this equation is solved for all of the different variables that we're solving for in our simulation. So you can see here, these different variables, essentially we're subbing these in for phi. Okay, so we're solving a pressure equation. So phi is P. We're solving our momentum equations for velocity in X, Y, and Z. And we're then solving also additionally things like turbulent production. So in turbulent production, we need our turbulent kinetic energy and our turbulent dissipation, epsilon. And these are solved for each of those control volume cubes or tetrahedrons, whatever our mesh shape is. Okay, so what we're going to do is we're going to go through the setup of a simulation. And then we're going to set it to solve, and we're going to come back and post-process it a bit later on. So the simulation we're going to be looking at is a FSAE vehicle, or just the front wing and the wheel, etc. So opening Fluent, for those of you who haven't already, if you just type Fluent into here, you want to get the latest version available, and you'll come to this launcher, okay? And you can see here that we've got our meshing. We can go straight into meshing, or we can go straight into solution. In this case, we'll go quickly into meshing so we can cover the basics of meshing again. It's important to, well, it's not that important, but it's really helpful to have our working directory specified as somewhere where we want our saved files to be and we want our reports to be generated. So I'm going to put it to the right one for today. And you can see that we can, in Fluent meshing, we can use multiple solvers, so multiple CPUs, which speeds up the meshing process. That's a new thing that's only come in fairly recent. Now you should all be familiar with this window. This is our Fluent meshing window. I will be very brief on the meshing things. If you do want to cover it in more detail, the recordings from yesterday will be up on YouTube, and we should be linked out. That link should be sent out to you guys. Okay, so we've got our meshing window here. Most of what we want to do in early days, as new users, will be in this window here. So we can select our workflow type, our watertight geometry. It used to be that all of our working was done in the outline view and in this ribbon bar up here, but now they've simplified it to make the meshing process a lot easier. So once we have our watertight geometry workflow, we can then move on. So there's the watertight geometry, or there's fault tolerant meshing. Fault tolerant provides a few more options and allows you to do some more advanced things with the CAD. So you can do things like wrapping, which is like, you know, if you're essentially going to cling wrap over something, it's going to basically walk over any problems in the geometry. So that can be really helpful if the CAD geometry you've got isn't super clean. So in this case, this is the CAD we're going to be looking at. This is really clean CAD. So we've obviously cleaned it up nice. So there's not really any discontinuities in the surfaces. There's no corrupted surfaces. There's no places where we have overlapping surfaces. All of these can cause really big problems for the mesher. So in this case, we can bring this in to our watertight geometry workflow. can see that's coming quite nicely. One thing to understand about Fluent meshing is the geometry comes in a kind of like an STL. It turns it into a TSV or TGF file. And that's basically, as you can see here, it's turned a continuous CAD into these tessellations. So it's like an STL, but a little bit different. And that's because Fluent meshing likes to deal with meshes and then remesh them. We're not going to add any local sizing at the moment, but what we're going to do is we go ahead and generate a surface mesh. You can see it's really helpful to see that the minimum and maximum sizings specified in here can be seen on the model itself. So you get a good sense of what kinds of mesh sizing we can be expecting. You can see that that's really helpful there. One thing that we would really want to do is to go back into our CAD model and check out our smallest kind of sizings. And we can see that probably our smallest sizing will be about 3.7 millimeters. Okay, so that's really important for when we come back into our mesher. If we really wanted to generate a high quality mesh and something that's going to resolve all of the flow field, all the flow characteristics, we'd want to have something that could step across that with at least 3 or 4 elements. Okay, so a minimum sizing of maybe 0.8 might be a more reasonable size for this simulation. But just for the example, we're not going to go that fine into it. Our curvature looks at how many elements we want over a curve. So you can see here that as this kind of curves around, every time it's gone 18 degrees change in direction, we'll put another mesh node. Okay, so that's just making sure that the curves are really well resolved. Once again, guys, I will ask that you mute yourselves, please, when you come in. It just makes it a bit easier for everyone else to hear what's going on. Okay, you can see we've generated a nice surface mesh here. Always comes in tets. And what we might do there is to have a look at the quality. So the maximum skewness is 0.9. So we can probably get that a little bit better. We really don't want to see a really high maximum skewness on the surface mesh, because the surface mesh is generally pretty easy to get a good quality mesh. A maximum skewness of about 0.6 is really what you want to see for a high quality CAD. And then in here, we want to go, there's only fluid regions, no voids. We don't really have any fluid to fluid boundaries because we've only got one solid body. Do we need to apply shared topology? No, thanks. Update boundaries, this is good. So we can change all of the boundaries that have been named in space claim to either walls or velocity inlets, pressure outlets. That's really helpful because when we put our inflation layers or our boundary layers, we only want them to grow on walls. So it's really helpful that these come in automatically named, and they basically, it's a little bit of intelligence built in there to pick out our named selections. So Ashan would have went through these yesterday, but you can see that the solver looks at each individual surface that has been named. Okay, so this one's named inlet, so it knew that it wants to be a velocity inlet in the mesher. Okay, so it's really important that in space claim, once we've finished generating our enclosure, we go through and name all of the separate boundaries that we want to be separate. So you can see here that the chassis is all of these walls here. If we wanted to break it down further and have the forces or the pressures looked at on, or a separate boundary condition on these front faces alone, then we'd put a separate boundary condition in there. Okay, so there's going to be a different boundary condition for each named selection. It's one fluid region, and then we can add our boundary layers, and that's going to grow only on walls, and then generate volume mesh. So it's a very simple process to go through meshing. I won't go through the meshing today in full. Like I said, go through Hashan's training yesterday, as he covered it in a lot more detail. But what we're going to do is we're going to take a mesh that we've generated earlier, and we're going to set that model up to solve. So we're going to go into solution. What was that? In 3D, we don't need double precision for today. That can be handy for getting extra accuracy out, but it does take longer to solve. Some helpful things in here, getting recent files that we've already accessed open. But we're just going to open it through here. We are actually on, this is, you might have seen, we're on using version 2020 R2. The most recent version is 2021 R1. So if any of you are thinking about downloading the software, getting a student version of the software, make sure you have the most recent version. They're constantly updating the software. So a couple of questions I haven't addressed. What angular resolution do you recommend for a production run? Meshing is a really difficult one to provide any hard recommendations. So basically, one of the most important things that you need to do in CFD is to always be conducting mesh independent studies. So if there's ever a concern about exactly what angle or what mesh size to run with, we can always start with the defaults, set up our run our solution, and then come back to the meshing, change some of those values to make sure that we're getting different mesh. Usually we'd be going for a more refined mesh, and solving the model again. And so what we're looking for is good convergence behavior, so high quality mesh. And also we're looking for the mesh, our solution variables, so things like our lift or our drag in this case, to be not changing with an increased mesh density. Okay, is double precision always the safest option? Yes, it is. If you're ever concerned, just put double precision on. I'd leave it off when things like this, because I don't need to use the extra RAM or use the extra time. We will be going through the inlet conditions, of course. There is backward version capabilities for Fluent, but not for Workbench. Okay, so I can open Fluent case files with earlier versions, but I can't open any older Workbench files. We'll go through Workbench in a minute. Okay, so our Fluent window is open, and we're going to read in our mesh that we generated earlier. And the first thing we want to do as a CFD engineer is to check out the mesh and make sure that it is of a high quality, and that we're not too many mesh elements for our current computing power to be able to solve. Okay, so this is the Fluent window for those of you who haven't seen it, the Fluent solution window. Basically, everything you need is up in here, this ribbon, or in the outline view. So there's really two of everything in most cases, and you can either run through things step by step in the ribbon view, or you can run through everything step by step in the outline view. Okay, so let's have a look, make sure our meshes come in as we wanted it. Looks like the right model. Okay, if we put our edges on, we can start to have a look at the mesh. So you can see that we've got a polyhedral mesh at the boundaries. We've also got our hex core in the center. So we've used polyhex core. So polyhex core, as Hashan went through yesterday, is a really great mesh type as it allows for high quality mesh near the surfaces. So polyhedral, because of its shape, can be a little bit better than tetrahedrals for getting a nice high quality mesh in terms of your orthogonal quality, and having a hex core in the bulk flow field is really good for a sped up solution. So I'll just show you the mesh through the middle. So you can see here that we've got our polyhedrals at the surfaces. So they're obviously more versatile. They can conform to any shape. And then we've got our hex core in the bulk flow field. And our hex core in the bulk flow field is really good for a sped up solution. It's just a more efficient way of solving the flow field numerically. Now, one of the problems with polyhex core is you can see that the hex core has what's called a 1-to-8 octree transition. Okay, so you can see that these squares move into a much larger square, and that transition can sometimes be a little bit of a problem for numerical stability later on. So when we start looking at our residuals, start looking at convergence, we have to start looking at areas like that. But otherwise, polyhex cores a really great mesh type to use. Okay, so what else can we look at when we're looking at our mesh? We really want to know the quality. Is the quality of a high enough level for us to be confident that our solution stability is going to be independent of the mesh quality? So one of the problems that you can have is with a really low mesh quality, you can have divergence issues or convergence instability purely due to skewed elements, poorly shaped elements that aren't capturing the flow field very well. So as Hashan went through yesterday, your minimum orthogonal quality is what we like to use the most. And in here, our minimum orthogonal quality is 0.18. So that's quite good. Okay, so we really say 0.15 is really good. 0.1 is getting towards the limit. Anything less than 0.1, we really want to get a bit better than if we can. Sometimes our geometry is really complicated. There's a lot of sharp angles and things. So it's not always possible to get a 0.15 or a 0.18, but that is what we're striving for. Would polyhex core be appropriate in supersonic cases where shocks will penetrate into the bulk flow field? That's a difficult one. Sometimes with supersonic cases, it can be really important to have your mesh elements kind of aligned with your shocks. So in that case, no. Generally, you might want a tetrahedral grid or some kind of structured grid where you kind of shape, you can have partitions in your grid that are basically at the same point as the shocks are expected to be. So not always polyhex core would be great for supersonic cases. So we get our mesh quality at 0.18, that's good. Our size, so we've got 1 million elements, just over 1 million elements. It's not too bad. For a model like this one, really I would expect in terms of having a result that's independent of the mesh density, you probably have cells, a number of cells in the range of 20 million before we really started to be confident that that our grid wasn't too coarse. Okay, so we'll go through the top bar today. We don't need to look at zones. So zones are our cell zones. So we've got one solid object in here that's been discretized into these mesh elements. So you can see here, one cell zone. You can sometimes have multiple cell zones. Say if we were doing a conjugate heat transfer case where we had fluid bodies and solid bodies, they'd be split up into separate cell zones. We don't need any mesh interfaces because we don't have separate cell zones. We don't have any dynamic mesh or mixing planes on. So dynamic mesh is really good for transient cases where we want to have our components in the flow field moving in time. We don't need any of this stuff, so we can move on to our physics tab. So our solver types, you can see we've got a pressure-based solver. Pressure-based is what will be used the majority of the time. Density-based solver can be used in cases where we have hypersonic flow. So in cases of higher than Mach 3, we want to be going to density-based, but anything lower than Mach 3, we're using pressure-based solver. Absolute velocity formulation and steady state solution this time. So in our models now, we don't have any energy turned on because we're not looking at temperature. So anytime you want to have a temperature in the flow field or some kind of heat generation, you need to turn on energy. So remember, if we go back into our RANs, Reynolds average Navier-Stokes equations. So each one of these variables is being solved in this RANs equation. So when we turn on energy, basically we're turning on this equation. So E, I don't know why it's in H in here. It's usually specified as an E instead of phi. So our transient convective equal to our diffusion generation in terms of our energy in the flow field. Okay, we don't need that on at the moment. You can see here we've got a bunch of other different models like radiation, multi-phase flow. So if we want to have fluids and gases, structural models, species transport. So that's where we can do our combustion, heat exchanger, discrete phase, so our particles, and our viscous. So viscous is just turbulence models. Turbulence models are a really important thing to understand with CFD. We'll go through it in a minute in more detail, but you can see here that there is a bunch of different turbulence models, and these are really important. It's really important for you to understand which model you're using and why, because they all do different things. Now, the most commonly used are K epsilon and K omega, and you can see here there are only two equation models. If we go back into here, our two equation models, we've got our turbulence production and our epsilon turbulence dissipation. So we're solving two extra equations, two extra sets of the RANS equations. Now, they are the most commonly used because they've had a lot of work done on them, and then are really well validated for industrial purposes. Now, if we wanted to go a little bit deeper, there's some other things. So there's the transition K omega model. So it's a K omega model, but with a couple of extra equations, one extra equation to try and work out the transition. It's usually a transition between laminar and turbulent flow. Same in here with the transition SST. So there's two extra equations. So what that's looking at is the transition between laminar and turbulence in the boundary layer. And as we'll go through later, capturing what's happening in the boundary layer is really difficult, but it's really important because that's going to tell you things like where your flow is separating, especially for cases like wings and wheels, where your flow separates. The exact point your flow separates is really highly has a really great effect on your actual aerodynamic performance, so your lift and your drag values. Getting into more higher fidelity models, we've got our Reynolds stress 7 equation model. It's quite in depth, and then we've got our scale adaptive simulations, so our detached eddy simulation and LES. So these are higher fidelity, as in they need a much smaller mesh size, okay, to be able to capture it, but they capture some really cool things. So, but we'll go through one of these models in just a minute. So can I comment on the minimum domain size to be used? Yes, I can. So it's really important that we have a large enough domain to capture the flow field. And so what we'd like to see is for a given flow velocity, you can see the flow will come in at a constant kind of, constant velocity across the cross section, and it will be disturbed by our geometry of interest. And we'd like to see that flow field return back to a kind of steady, constant value before exiting the domain. Once again, that is really a trial and error process a lot of the times. It's nice to have 4 or 5 body lengths behind the object. In this case, it's probably not as big as what we would like to see, but we are really only interested in the front wing. So one of the things this model would be built for is just to assess the front wing. So we might put a bunch of different front wings in there with the same chassis and the same front wheel to get a good understanding of the performance of that front wing. And so because it's only the front wing that we're really interested in, we're quite a few body lengths of that front wing behind. But once again, it's a trial and error process. If you run a simulation, you look at your post-processing and you haven't, the flow field hasn't returned back to a kind of steady, constant state before the outlet, then you need to go back to the mesher, go back to geometry, make it bigger, remesh, and bring it back in. Because one of the really interesting things, well, the things about fluid dynamics is that what's going on behind here can really have a strong effect on what's happening up here. So if we're not capturing it in the solver, how do we know we're being accurate? Okay, so in this case, we're using K omega. So K omega SST. So K omega SST is, once again, your 2 equations, and it's got a shear stress transport model, which looks at what's happening in the boundary layer with a bit more accuracy, okay, than some of these other earlier models. For grid independence, another question. For grid independence analysis for different turbulence models, should we use different near wall region mesh resolution? For example, with comparison to K epsilon wall functions with K omega SST. There are some idiosyncrasies with the different models, and I will cover those at a later date. But understanding what kind of Y plus value is really important. We'll go through what Y plus is in a bit, but there are some different grid resolutions that you would use for different models. Okay, so we're going to look at our materials. So in this case, we're just using air at a constant density and a constant viscosity. Okay, so if we turn on things like energy, we're going to get a lot more of those properties. If we turn on things like species, we'll get even more properties that are be calculated in our simulation. In a simulation like this, we only need a density and a viscosity. Constant density, of course, because we are below Mach 0.3, so anything above Mach 0.3, the compressibility effects of air play a part. And you can see here that if I turn on the ideal gas model, then we need our CP, our thermal conductivity, and our viscosity, because our density is now a function of the pressure and the temperature. But in this case, constant density. Constant viscosity, but there are a bunch of models that we can use for a variable viscosity, which might be really important in cases, once again, like high velocity or high temperature. In here, we can, there's a database full of different materials that have a lot of helpful material properties, which is really good. And you can copy those in, okay? Lots of fluids and solids. And once you copy them in, you can see them in here, and they can be applied to any of the cell zones in the model. Okay, user-defined can be used for user-defined functions. Oh, before we go on, we'll do our boundary conditions. So you can see in our zones, our boundaries, group them by zone type so it's easy to see, and we're going to set up our boundary conditions. All right, so in this case, we've got our velocity inlet. And we're going to simulate this flow coming in at about 40 kilometers per hour, 11.1 meters per second. You can see here we can change our reference frame. We can have different specifications, magnitude and direction, or components for our flow coming in. Because we've got a nice flat surface that is perpendicular to the flow direction, we can have magnitude and normal to boundary. We don't need any supersonic initial gauge pressure, and you can see here that our turbulence parameters, that's our flow coming in, will have a turbulent intensity of 5%, a turbulent viscosity ratio of 10. So depending on your application, it might be really important to get these turbulent intensities correct coming in, because they can have a really big effect on the force values. Higher turbulence is usually going to provide higher forces overall. Outlet on the back end, basically usually a pretty simple specification. Gauge pressure of 0, so that means it has no effect on the flow, and normal to boundary, etc. Once again, so a backflow specification here. Sometimes we don't want any backflow in a CFD simulation, so flow coming back in through the outlet, because that's flow coming in that hasn't been solved for anything. It has to be specified. It'll come in with these turbulent parameters. How do you calibrate the turbulence values? That's a really difficult question. Well, it's not a difficult question. It's a simple question, but it's very case specific. So if you're doing if you have a wind tunnel run and you're matching your values in your wind tunnel, you'd probably have a really low turbulence specification, but you might tune that turbulence specification to get the right values out. So if everything else you've got matches what's happening in the wind tunnel, and generally we want a turbulent intensity of around 1%, but the force values aren't quite matching, you can kind of calibrate that turbulent intensity to suit. I did a case recently where we did an atmospheric boundary layer, and that was specified using a log law function. And basically our velocity coming in was in the shape of something like this, because it's a atmospheric boundary layer, so 0 at the surface and increasing with increasing distance from the ground. And that's specified in the Australian standards as what turbulence values should be at what height. So yeah, so it can be specified, and also sometimes it might need to be calibrated in as a trial and error method. Okay, this is another question. In this type of simulation, are we assuming the entire model to be rigid? Yes, we are. Wheels will be rotating, so there'll be a velocity on the wheel surfaces there, and the ground will be moving. But I'll show you the wheel compliance and the VD, so vehicle dynamics, so your shocks, shock absorbers, and then they'll actually be dropping as well, depending on how high the fidelity of the simulation. In this case, generally it's a pretty good approximation to have everything solid. You can basically get a change the shape of the wheel. So if you work on, say, some images that you have of your vehicle going around a track, what the average kind of shape of that wheel is, especially where it bulges out down the bottom, you can build that into the CAD, but we won't have generally won't have a model that's changing in as the solution goes. Okay, that's a very complex model that requires things like your fluid structure interactions. But it's a really good question. It can be really important to have your tire shape be more accurate in terms of trying to understand what's happening to the flow in these areas. But it's always a toss-up. Do we need to go into that much detail? Can we do 10 different front wing iterations without having to change the front wheel shape and get a good understanding of the difference between the front wing designs, and still have a really good useful understanding of what's happening in that area without having to go to that much effort? It's always going to be a toss-up between accuracy and time spent on the simulation. For the inlet pressure condition, inlet boundary condition, are you able to set the value to vary? For example, head pressure across a large pipe under gravity flow? Yes, we can. Fluent is coming up, is updating its named expressions all the time. So in the latest release, they did some really great work with making these named expressions even more useful. And these named expressions can be used to specify varying inlet conditions. So basically, if we wanted to have a inlet that varied in velocity with the increasing distance from the surface, we might have 5 a second times y, and that should get us, that y is in meters, that's per second, meters per second. If I have a look at that, well, I'll have to put it somewhere. So if I go inlet, we can then change this velocity magnitude to an expression. What's it called? XPR1. Apply. And you can see here between 0 and say 4, that's what our velocity profile is going to look like. Okay, but in our case, we're not going to use an expression for, but that is those expressions. That's a very simple one. You can have those expressions varying in terms of what the outlet quantities are, in terms of what the temperature might be at certain points. They're really helpful functions that can be used to have a varying input quantity. How to avoid reverse flow? Some cases that's impossible to avoid reverse flow, but we need to make sure that our domain is big enough. Okay, so in this case, a big enough domain will avoid reverse flow, because by the time the flow has gotten far enough away from this vehicle, there won't be any more reversed flow due to the wake region of the vehicle. So having a larger domain will reduce the flow. Okay, so we're getting to some more detailed questions. In a blood flow simulation, can I give pressure boundary conditions to both my inlet and outlets? That is a case-specific question again, sometimes. Just specifying pressure at inlets and outlets can make for a poorly resolved solution. Not poorly resolved, poorly specified solution, and can make difficulties in terms of solving. So if you have trouble with your convergence, make sure you go to the support hotline, and we can answer the questions like that a bit more detail. Just to reiterate with the expressions, there's a bunch of different functions you can use. So we can use it and, if, not, or statements, mathematical functions here. Okay, so there's a whole load of different things that you can do. Okay, a lot of questions coming through, which I really appreciate, but there's a lot for us to get through. So try and answer them as best I can. Complex name expressions such as exponential powers just went through. What about avoiding reverse flow and internal pipe flow? Sometimes, like I say, it's not able to do. Sometimes it's not such a big deal. It depends on your the size of the domain. Obviously, you're solving for the physics of the problem. So if the flow characteristics are the function of the physics, you can't necessarily do anything about it if you can't make the domain big enough that you're not getting reverse flow, or the setup of the situation is such that there's always going to be reverse flow. Sometimes you can't avoid it, and that's okay. But in cases where it's unnecessary, like this one, where we have a wake region that if we don't capture the full wake region, we're not going to get an accurate understanding of what's happening here. We don't want to have reverse flow, but in certain cases, it's unavoidable. Okay, so in terms of velocity inlet or pressure inlet, you can change the type here to a pressure inlet. And our gauge total pressure, that's our pressure above or below the absolute, no, what's the what's the value? So we'll have a value here of, that'll be our atmospheric, 101, 300 pascals. And our pressure above or below that will be our gauge pressure. So our gauge pressure plus our reference pressure will be our absolute pressure. So gauge pressure is just above or below what the average pressure, or what the reference pressure, not average pressure, the reference pressure in the simulation is. Yes, we are able to do custom materials. So you can change this to 5 and change or create, and then so they're all able to be edited. Can we trust the results having reverse flow in 80% of the region? That's very case specific. You'll have to go to support for that one. You can just give a static pressure to your inlet, but it will be in terms of a gauge pressure generally, because we generally don't talk about static pressure as an absolute value, which is what it actually is. So in reality, we've got our atmospheric pressure, and any pressure that's forcing flow in a pipe will generally have something above atmospheric pressure, but we can just specify the gauge pressure. Okay, so our inlet and outlet done. Our symmetry condition. So basically, one way of reducing the amount of mesh elements in the domain is to cut it in half. And that's what we've done in this case, because our flow is coming in straight on. So because our flow is coming in straight on, it is symmetric. So we can have our symmetry boundary condition at the wall there. If you ever are interested in you know, more mathematical specifications, or you need more information when you're using Fluent, if you type in help in here, wherever Ansys is installed, you get this Ansys help document. If you have it installed locally, it'll look like this. Otherwise, it'll come up online and look like this. I'll have to sign in, which I'm not going to do right now. But yeah, in here is really helpful. You can go into what's your symmetry condition, what that means in terms of a fluent flow. So we go into here, deselect, Fluent, update. So this is really helpful if you're doing any projects at uni and you need to write your reports. So this is just some applications, but if you go into the theory guide, there's symmetry boundaries in the theory guide as well. We'll discuss it in different ways. So there's two different two main sections that you'll be looking at. Is your user's guide that provides some really helpful tips and tricks on how to use specific models and specific boundary conditions, and our theory guide, which goes more into the theory. But if you ever want to be a good CFD user, get used to using this manual, because it's, yeah, all of the information, well, not all of it, but you know, the majority of information you're ever going to need is in there. Can we get a fully developed velocity profile at an inlet by giving pressure inlet boundary conditions? If you want a profile to come in fully developed, generally you'll have to specify a profile. So that can be specified as, you know, X and Y locations and the velocity at each of those locations, or the pressure at each of those locations. generally, to get the flow field fully developed, you'll need some space away from the inlet to allow that flow field to develop before it hits the vehicle, before it hits the the region of interest. But yeah, a fully developed flow field straight at the inlet will usually require something a little bit more than just a pressure or a velocity inlet. And you can do that by specifying this as entering a profile. So in here, we can enter a profile. So we could essentially take out the profile at the outlet. So if we wanted to use the outlet profile of one simulation as the inlet profile of another, we can take out a profile from the outlet and specify it as a profile for the inlet of the other. So that can save us on computational expense by not having to have the inlet so far from the region of interest, because the that space might be necessary to allow the flow field to develop, to fully develop before hitting the region of interest. It's obviously really important for things like flow in a pipe. Less so important for simulations like this, where we're really expecting, because the flow is in reality and we're driving through it stationary, as we see it, the flow has a constant velocity coming towards the vehicle. And so in this simulation, we don't need a fully developed flow field. We could even have the inlet a little bit closer, as long as it's far enough away that when the velocity profile starts to change due to hitting the body, we're not within that region. We're a little bit far enough away that we've got a constant velocity profile before it starts to change. Okay, so in a simulation like this, when we're really interested in the forces on a front wing or the forces on a chassis and the wheel, when we're operating so close to the ground, we really need to have an accurate understanding of what's happening between the wing and the ground. And one of the things that's happening in reality is the ground is moving with reference to the wing, and that can create things like ground effect. And we can make sure we capture that by changing the specification, the motion specification on the wall. So if we change to a moving wall, generally with all the other walls, we don't need to change anything, but in this one, we can change it to a moving wall and have a translational in the -Z. And we want that at the same speed as our inlet. Our wheel should also be rotating. So we want to be going about the x-axis. We should get the actual value for the location as well. So radius of 228.6 and a speed of 11.1 meters per second should give 49 radians per second, if I'm calculating that correctly. And our position we can get from here as well. Showing X, Y, Z. So we want our -Z with that one, 898.67. And our Y position is 225.6. Make sure we have it in the right units. And that's going to be about the positive x-axis. So that's how we specify a rotating wheel. For a 3D cold flow case, does symmetry and zero wall shear stress boundary conditions on the enclosure provide same result? For most conditions, symmetry and zero wall shear will provide us the same result. Can you map fields? But once again, go into the help file, get the actual mathematics specifications to ascertain that before you use it in your in whatever project you're doing. Can you map fields from a coarser mesh to a finer mesh to provide initial conditions and thus speed up convergence? You can, yes. One of the things we can do is an initialization that we need to do for every simulation, and we'll go through what initialization is, but that can do something very similar to that in terms of solving on what is essentially a coarser grid to get a good initial guess, and then we start to solve the RANS equations for the full fidelity mesh size. Okay, so this one is all the boundary conditions are done. So we've got our moving ground, we've got our rotating wheel, we've got our flow in, and our flow's allowed to go out. Our top wall should be a zero slip. Oh, it's a symmetry. We can leave it as a symmetry. So that's fine. This user-defined functions section is much less useful now that we have named expressions. These have only come in the last few releases. Remember, these are the way we can specify operations where the inlet condition might be a function of the height, where the thermal conductivity might be a function of the current temperature, things like that. So the current local temperature. So these user-defined functions used to be the only way we could do that. Now we're able to do it through these named expressions. But if there are some things that can't be done in the named expressions, user-defined functions can still be written out. These are written in C code and specified and compiled through the compiler in Fluent. Okay, so with all of our boundary conditions done, our mesh is good. We can have a look at our solution options. In our pressure velocity coupling scheme, we're using coupled. There are some options for simple, simplec, and piezo. The major difference is between coupled and simple or simplec is the coupled solver solves your in your RANS equations, your X, Y, Z momentum and your pressure all in the one go. And in your simple solver or your segregated solver, it solves separately for your U momentum, V momentum, W momentum, and your pressure all separate. So coupled takes a little bit more RAM per iteration, but should solve faster and should be more robust. But we'll go through that a little bit later in more detail. Named expressions can be time dependent. Yes, they can. Our spatial discretization for each of our gradients, for our pressure, for our momentum. So that is, our discretization, our difference between the cells, how we're calculating our gradients. There's some options in here. Second order, it's usually fine to leave the defaults, and that's what we'll do in this case. We might discuss these in a little bit more detail in later parts of the session. And it's now a default that pseudo-transient is on. So pseudo-transient is a method of under relaxation where it breaks the solution down into a pseudo-transient time step. Once again, go into the help files to check that out, but that can be really helpful in terms of getting a more stable solution. So one of the difficulties that we have in CFD generally is that, especially for a case like this and for all cases, fluid dynamics is highly nonlinear and it is highly transient. Okay, so every time we're trying to say run an 11.1 meters per second wind over this vehicle and get a steady state result, we're often not able to get a steady state result exactly because it's not a steady state flow phenomena. So when we have if any of you understand things like vortex shedding, von Karman's effect, you understand that a constant flow field can produce time-dependent results. And in a case like this, where we've got lots of curved surfaces, rotating wheel, really likely to have some kind of time-dependent effects in the flow field. Pseudo-transient tries to under-relax for those kinds of things, which means just to stabilize those kinds of things, those kinds of transient effects, so that we can get a reliable, steady state result. But there are some things that we need to do in our in our convergence monitoring that will allow us to make sure that we are doing our best to get a steady state result from a transient solution. So our pseudo transient is a really good method of doing that. And you can see up here our time scale factor, that's from the pseudo transient being selected on. So we can change that to our 0.1 or 0.01, depending on our convergence behavior. So everything there, we've had a bit of a discussion, but we've just left it all as default. And that is generally all you have to do for most simple cases, but as we get more complex cases, it can be really helpful to play around with those. Our pseudo-transient explicit relaxation factors. So these are different relaxation factors to pseudo-transient itself. So these are there with or without pseudo-transient being ticked on. And what these are, we'll go through at a later time as well, is that so we're solving an iterative solution. At iteration 1, there's a value for pressure. At iteration 2, we've calculated a second value for pressure. An under relaxation factor will take half of that difference rather than take iteration 2's value. And that will basically allow us to converge more stably to a solution. Okay, so for our second iteration, we got P2, and that difference between P1 and P2 might be really large. And if we take that whole value for pressure 2, we might get oscillations and difficulty in convergence. So we use under relaxation factors to allow a solution to converge more easily where we're seeing that it is being unstable. Okay, so we can play around with these once we've run our solution and assessed the convergence behavior. So in our equations in here, our flow equations, that's our U, V, W, momentum, and pressure. And our turbulence equations, our K and epsilon, or K and omega in this case. And we can turn those off or on depending on what we want to solve for. Generally, we don't really play around with them, but the option is there. Now, what we're going to do in here, our residuals. You can see here that our criteria for all of our residuals is 1e to the negative 3. That's the default. Now, what residuals are is our difference between our right side and our left side of the equation. So our transient and convective should equal the diffusion and generation terms. If they don't, there's a residual. Okay, and that residual, the larger the residual, the less converged we assess our solution to be. Okay, so 1e to the negative 3 is usually pretty good. If we can get it below that, we're doing well. So we'll leave that as default for now. But another way in which we assess convergence, so remember what I said, fluid flow is highly nonlinear and highly transient. So getting those converged residuals down below 1e to the negative 3 is sometimes really difficult. And so another way of assessing convergence is using monitor points. So these definitions in here can be used to generate monitor points. And usually they will be something to do with the output quantity of interest. Okay, so in this case, one of the major output quantities of interest for somebody who's designing a vehicle like this would be downforce, right? So we want to maximize downforce, or we just want to have a really accurate understanding of downforce. So if we go into here, we create a new definition, force report, lift, call it downforce, lift force, not coefficient, and on all of the surfaces we want to understand that force from. And then we end the wheel. We'll put that in negative y because we want to know how much downforce, not how much lift. And create a report plot. And we can also generate a report file if we want to do our own post-processing with that later. And we'll print that to console, which means it'll come into this TUI here. Okay. We'll create another one for drag because that's just as important for most vehicle designers, aerodynamics vehicle designers. Call it drag. Everything but the ground. And that should be in negative Z. Report plot, print to console. Okay, so those two are what we will use. Another one that we could use is maybe a surface report of a standard deviation of the velocity field on the outlet. So if that value's up and down still, then we haven't got a constant flow field for the amount of iterations that we've done. So outlet, if I can spell, and standard deviation, same again. Okay. Got a few questions. I'll just address those before we move forward. Must I know C code to enter in user-defined functions? So go back to these user-defined functions. If we can't get the utility out of the named expressions, we can use user-defined functions, and they are written in C code. You do need to have a bit of a grasp on it is helpful, but you can get examples of code out of this customization manual. You can see that these used to be, these are the bits of code that we would use as a user-defined function rather than the expressions. And you can see they're in C, but they will give you examples. So yeah, going into the help files, getting a good understanding of what's in the help files will allow you to, utilize all this information better. How to simulate flow of a vehicle in a corner. Really interesting question, quite a difficult question as well. A couple of ways we can do it, depending on how simple or high fidelity you want to go. Obviously, we can't have a symmetry plane anymore because the flow is no longer symmetrical when it's coming from an angle. The simplest way is to just have a box domain and have inlet, and just have some angle of the flow. And you have outlet. And you'll turn the wheel, maybe you'll put some roll and pitch on it, depending on what vehicle dynamics you're expecting to experience in a corner like that. Another way you can do it is you can have a rotating domain. So you can have a kind of annular shaped domain, ring shaped. You wouldn't have the whole ring of it, but enough that the flow's coming in at a circular angle. If that makes sense. They're much more high fidelity. So when you're doing flow, any yaw angle on an aerodynamic on a vehicle is much bigger because you're doubling the amount of elements you're using. Pseudo transient relaxation factor is there's no way to tell exactly what it should be. Once again, you can do things like you can calculate how long you would expect it to take the flow to get from the front of the front wing to the back of the front wing, based on the flow velocity and the length of the front wing, and then divide that by 10, and then that might be a in here, sorry, you can change the timescale factor to being user specified as a time value. And then you can specify that as that, value divided by 10 for the time it would take. You would expect the flow to take to get from the front of the front wing to the back of the front wing. But once again, trial and error. There's no way to answer that question. So, hey Errol, since we have symmetry, are the monitors giving us drag and lift for the whole vehicle, or manual times it by 2? You'll have to manually times it by 2. Is it accurate to have the same Y plus values over this entire car, even though different parts of the car can be considered to have different hydraulic diameters? Good question, and there is no way to answer that question 100%. You can try and be a little bit tricky with, having different specifications of Y1, Y plus heights in your boundary layer for different sections of the car, but there's no way to be, generally we would just go for a value that gave us a really good Y plus in our region of interest, and maybe less so in areas that we don't as worried about. So in this case, we really would be worried about the Y plus on here and here. Our Y plus is our first cell height. We'll have to go through that when it comes up in the slides. But yeah, having a you'll never get it perfect, and doing your mesh independent study is the only way for you to know properly. And you're right, characteristic length would be a better way to say that. Is it possible to introduce deformation of the element during the simulation? Yes, it is. We'll go through those, some of those methods a bit later on. Okay, so we've specified our monitors, our convergence monitors. Then we can move into our initialization. So obviously with an iterative simulation, we need to have an initial guess. So we need to start with, a value in each of these cells. Hybrid initialization is usually pretty good. And when we click initialize on that, we can see that it'll run through 10 iterations and give us an initial starting guess, and then we can start our solution from there. We'll go through the initialization in more detail in the slides, but there are a few other methods. So standard will basically just pop a value in the cell that we ask it to. It doesn't go through any initial iterations. And our another more advanced method of initialization called FMG initialization will break the domain down into, it'll group elements together and consider each of those one element. So it starts with a really coarse grid, solves the flow field for a really coarse grid, and then you can move to the solution from there. So that's the best first guess, takes a little bit more time than the others. You can see hybrid initialization takes some time itself, right? So just to get these 10 iterations and hybrid initialization done is a bit of a process. Now though, we can start our solution, but let's just have a quick look at what it means to have done a hybrid initialization, because now we've initialized, we actually have solution quantities in all of these cells. Okay, so we can do a little bit of interrogating to see exactly what what's initial first guess we've got on our hands. So it's pretty constant pressure at the inlet boundary, not the inlet, sorry, at the symmetry boundary. And same here. So that's our pressure. What's our velocity look like for these surfaces? So we can see we've got some varying velocity. It's done a pretty good job. We know that that's going to be faster in there. But this is a really good way of understanding, okay, what's our first guess? Because for difficult problems, our first guess can really have a big effect on how quickly we're going to converge. Okay, so and sometimes whether or not we converge at all. So if we were to do standard initialization, you can see in here, we're just specifying these values for all the cells in the domain. So that's, so in all of these cells, we'd have a velocity of negative 11.1. And that would be our worst first guess, but would be a quicker initialization. So we've done our hybrid initialization. That's what it looks like. We're going to make our we're going to leave our timescale factor as 1, and we're going to run for 500 iterations, and we'll just let it go. Let's just have a look at what it looks like when we're solving before we move on. So you can see one iteration, each iteration is printed to the console down here. And we've got a residual value for continuity. So that's our mass flow versus mass out, mass in versus mass out for each cell. Our X velocity, each cell, Y velocity, Z velocity, K and omega. Now remember what they are. They are the difference between the left and the right-hand side for our Reynolds average Navier-Stokes equations. So we've got our continuity, our momentum, and our turbulent production, turbulent dissipation, in our case, omega. We don't have any energy solving in our case. So what we want to see and what we specified is an expected convergence of 1 e to the -3. So you can see here we start at e to the -1. This one's already pretty well, pretty low. X, Y, and Z. K could do with a bit more convergence and a bit of reducing. And you can effectively just watch those go down. Now remember, highly nonlinear, highly transient, the flow field. Often you'll get to a point where these residuals will not converge any further because we're trying to get a transient solution from a steady state. And we can do things like change the under relaxation factors, the timescale factor, which is the pseudo transient relaxation factor, or the other under relaxation factors which were in here, pressure, velocity, etc. But often, it's not always going to be a guarantee that we get a converged solution. And the other way that we can assess convergence is through these monitor points. So obviously, if these monitor points are still, jumping around all over the place per iteration, so it's not converged to a solution, then maybe we need to do a bit more work to get a solution converged. So sometimes the residuals won't necessarily be below 1 e to the -3, but if our downforce plot looks dead flat and our drag plot looks dead flat, obviously as it's gone on with more iterations, then maybe we can consider our solution to be converged, okay, without necessarily getting our residuals down, because our residuals may not go down because we're trying to get a steady state solution for a transient problem. But all of that is, once again, very case specific, just some things that we need to understand for basic CFD when you start doing your own projects and things into the future. A more thorough investigation of all of your convergence properties and convergence behaviors is necessary for you to make sure that you're getting as accurate a result as you're using the tool in exactly the best way possible for your simulation. So we're going to leave this one to solve. We're going to have a little break, maybe take half an hour or 20 minutes, sorry, take 20 minutes. When we come back, we're going to go through turbulence modeling, so in more detail. And I'll show you a case that I set up for a client that was looking at aeroacoustics of a mouthpiece for a sleep apnea mask. Like I said before, we're going to have a look at turbulence modeling in a bit more detail, because I think that's really important to understand. So what is turbulence? Turbulence is is a chaotic flow phenomenon. And really, one key point is all flow is turbulent. No flow is purely laminar, even flows that really seem laminar. At some level, there is some disturbance in the flow field. It's not a perfect free stream, everything in a straight line velocity, but there are situations in which we can model things as laminar flow, and situations in which we need to really account for turbulence. So you can see that there's laminar flow, transitional flow, and turbulent. And that is a flow through a pipe and a bit of dye being let off. And you can see that with highly turbulent flow, there's a lot more mixing. It's a really important property of turbulence. And these three things are highly dependent on what's called the Reynolds number. The Reynolds number up here is our ratio between inertial forces to viscous forces. So inertial forces are the inertia of the flow, so the velocity, things like that. You can see that velocity is on top, the density is on top, so our mass, and the length of the characteristic length is counted into the inertial quantities, and it's inertial over viscous, and so below is the viscosity of the fluid. So the higher the Reynolds number, the more likely it is to be turbulent. And Reynolds number is just a non-dimensional quantity that is an attempt to allow us to classify a specific what's called regime of flow. Okay. So in this case, you can see turbulence modeling, turbulent boundary layer on a flat plate. This is an experimental model done by some of the guys at Melbourne Uni, I believe. You can watch that YouTube video because it actually shows it happening live. On the top, we have a flat plate moving in the flow field, and on the bottom, we have the same thing at a different velocity. So you can see that the velocity's changed and the Reynolds number's changing. That Reynolds number is actually updating with time as we move further along in the characteristic length. And this streamwise distance is that length. And so the important takeaway from here is obviously two different Reynolds numbers based on two different flow velocities at the same point, totally different flow regimes. Okay, so this one you'd probably classify as having smaller turbulent structures. You can see that each of these turbulent structures, which are often vortices, most of the time are vortices, and probably a bit more chaotic, whereas this is less chaotic, larger turbulent flow structures. Now, the reason it's really important to get this right is because in order to calculate for turbulence directly, it takes really, really high amount of mesh elements. Okay, and a high amount of mesh elements means a higher amount of RAM, higher amount of CPU power required to solve a simulation. And that's most notably seen in DNS. So DNS is direct numerical simulation. Essentially what we're doing with DNS is solving the RANS equations. So we're solving for pressure and velocity without K and epsilon, without K and omega, directly solving through the RANS equations. And we'll use things like a higher order spatial discretization as well. So between the cells, we have our spatial discretization. Usually we use about second order. In DNS, we're using up to fifth and sixth order spatial discretization. So it's a lot more computationally intensive and is not practical for really any applications other than research. So it becomes really important to be able to capture this kinds of, the bulk effects of the turbulence in a averaged manner, because then that allows us to get a higher level of accuracy. So we'll go further into what it means in the boundary layer later on, but one example of that is if we were to model this here, we'd need to pick up this turbulent vortex structure, we'd need at least, say, 10 mesh elements across that thickness, across the distance of that vortex in order to pick it up properly. Whereas in this case, in order to get an accurate resolution, we need maybe 2 or 3 elements across the same thickness. And in a boundary layer, that's where we're having some really important effects of turbulence that can cause separation. And so having a really good RANS model that can make assumptions about the turbulent structures is really helpful. So, but in between those two, we've got our LES, a large eddy simulation. And so what that does is solves the filtered equation. So it allows for picking up of these larger turbulent structures, but won't necessarily model the smallest turbulent structures. Less expensive than direct numerical solution, but the effort and computational resources needed are still too large for most practical applications. So that's why we use K omega in the in our car model and for most other applications. So all in RANS modeling, all turbulence effects are modeled, so not picked up directly. So you can see here that turbulence is really the deviation from the mean flow. So if we had a point in the flow field here, because we've got kind of, say, time varying effects where, you know, these kinds of vortexes look like they're kind of shedding off, we're getting oscillating flow. There's a bulk flow field that's getting picked up here that you'll pick up in a RANS equation, but you're not going to pick up all of the deviations. Okay, that would be, you would need a LES or a DNS model to get those smaller fluctuations off the mean velocity field. So these are the different models. So we start with the lowest fidelity. We've got our one equation Spallart-Almaras model, our two equation models, K epsilon, and a different family of K epsilons, the standard realizable, and our K omega family, which has our gecko and our SST, which are really important, which we'll go through in a bit. And then into some more advanced models. So looked at before when we were setting up. So we've got our Reynolds stress model, which is 7 equations, our transition SST, detached eddy simulation, stress blended, and a large eddy. Transition SST is a K omega with a couple of extra equations that tries to pick up the transition between laminar and turbulent flow in the boundary layer, because that's going to give us a more accurate understanding of the adverse pressure gradients in the boundary layer and a better understanding of where the flow is going to separate. Once we get above these, we're into our scale adapted simulations. So DES, SBES, and LES. So those are the ones in the middle of the graphic here. So if we look into our help files, you can see that this is how the K omega equation actually comes up in the RANS models. So you can see that there's a basic shape to it. Our transient and our convective terms must equal our diffusion and our source terms. Okay, that's for our K. And for our omega, which is our turbulent dissipation, we've got our transient and our convective, which must equal our dissipation and our source terms. And you can see that in the help files here. One thing I will mention really quickly is the gecko turbulence model. If any of you are interested in doing a CFD project that you're not already a part of, and you find that there might be a way for you to use the gecko model, I would definitely recommend doing it. Basically, the gecko model is the K omega model, but it's kind of modified slightly to have some different parameters that you can tune. So when we go back to here, so there's some parameters that kind of fit into these equations, especially into the source terms here. That in K omega SST, the standard K omega model, you can't touch them, because if you touch them, everything's thrown out of whack. K omega is built in such a way that you can get these, you can calibrate certain parameters, which are these ones, to get different changes in the flow field. Okay, so the functions F1, F2, and F3. So you can see here our transient, convective, always the same shape of equation. And we're looking at these C-SEP, C-mix, CNW, near wall, C-jet. And they're basically in these equations here, and you can modify these without changing some of the other properties. So in the other case, you can't modify the coefficients because you'll mess up the whole model, where in this case you can kind of change the values. So we're looking here at changing C separation and having these different values changing for each C-SEP will give you a different velocity profile at the wall at this point based on those values. Okay, so some really interesting things that can be done, especially if anybody's in the FSAE teams and wants to do, especially say at Monash, if you've got access to the wind tunnel and you have the ability to look at the flow field at a given velocity, match that in CFD, and try and match things like velocity profiles and separation points using the Gecko model. What you can then do is you can use those coefficients that you've decided on. So Gecko 1 is Gecko with a CSEP of 1. And put them onto your other model where you're not matching up against your wind tunnel. You're actually looking at, you know, the performance of the vehicle around a track. This can provide you with a much higher accuracy because you can calibrate the model for the wind tunnel application. So you know that you're getting good values for your mesh density, good values for your geometry, your vehicle geometry, and then take that to the rest of your models, which you can't necessarily validate, but you now have a better idea that it's going to be accurate based on the calibration that you've done. This is C near wall. So we've got a backwards facing step where the flow kind of separates at the wall and has to reattach at some point based on the different values of C and W where the flow reattaches. Okay, and the coefficient of friction at those points. Okay, so that's your Gecko model. I won't go too much further into it, but I think it's really important that we understand that that you guys understand that it's possible to have a RANS model that you can tune now. And if you want to do a project on it, I would highly recommend it because it's a very new model. It's only come out in the last year and a bit, and so could be really valuable for a university project and also for things like your FSAE teams. Okay, so I will go through the setup of another model now. We won't solve the other model, but what we're doing is we're going to look at a model that uses a SBES, so stress blended eddy simulation. So that is one of these. You can see that it's in the higher order range. And what the stress blended eddy simulation does is it allows us to use an LES model in the bulk flow field. So go back to this graphic. So an LES model in the bulk flow field to pick up the kind of turbulence, the larger turbulent structures, but it uses a RANS model at the walls, because at the walls, to use an LES model would require a lot of mesh elements because the actual major turbulent structures near the walls are tiny. Okay, so the whole point of an LES model is you need to understand where the most energy is going into what size turbulent structures the most energy is going into. Near the walls, the most energy, turbulent energy in the flow is going into really small turbulent structures. So having a stress blended eddy simulation allows us to use RANS at the walls and LES in the bulk flow field. And I'll show you how to set that up and the reason we would use that. Sorry, I missed a couple of questions. I can't see your questions come through when I'm on the present mode. What are programming languages for UDF in Fluent and Ansys? It's always C. Programming language is C. 2D simulation of natural cooling of a heat generating solid body in a closed container filled with oil is possible, question mark. Should I give inlet oil velocity as 0 in such case, or is there no need to give an inlet outlet boundary condition? Very case specific. I can't cover too much specific stuff here. There is an example here of a free convection, so a heat transfer. You can see there's a hot body. That flow will so heat generates a difference in density, which can create buoyancy effects, and free convection will take flow away. How to specify the boundary conditions for that, maybe going through this tutorial here would be very helpful. You involved with the experiment at Melbourne University. That's really cool. I was really impressed by that work. So that was great. What if my viscosity is changing throughout my flow channel due to temperature gradients? We've been through that. Make sure that if you've missed the first part of the session, you go back through and have a look. But in our materials, our viscosity, you can have that as a function of, as a piecewise expression, as a polynomial, as an expression. Remember, we've been through expressions, or using some of these other methods. Sutherland is a way that it automatically specifies as a function of temperature and pressure or density, etc. So the use cases for K epsilon and K omega are anything. Most industrial flows will use K epsilon and K omega, unless you need to do something like this aeroacoustics case. Now, before we go into this aeroacoustics case, which is using the SBES method, we're going to look back at our convergence behavior of our model. Okay, so this is our vehicle model, just to remind everybody what it looked like. Angus, how do we choose between K epsilon and K omega? That's a difficult question. Depends. It's case specific. Most external aero flows, I'm going to use K omega SST because K omega SST, the SST stands for shear stress transport, and what it is a really good way of picking up what's happening in the boundary layer, which we'll go through in a bit when we go through boundary layer modeling. K epsilon's also pretty good. It has enhanced wall functions that do similar things, but K omega is the most validated and the most highly recommended. But yeah, often you'll find that your research group at uni will have a preferred turbulence model, and that might be based on previous research that they've done where that model married up better with the solutions, and there's no right or wrong answer to it. Multi-phase mixing K epsilon, I think K omega is just as good for it. So K omega is K epsilon in the bulk flow field. It just has the shear stress transport model near the walls. Once again, these are questions between the two. I can't answer them. It takes research. Your research group will have a preferred model based on previous work done, things like that. So yeah, it's a question that's unable to be answered on the spot like this. Okay, so let's go through the convergence behavior. Like what we let's assess how the models run on this one, and maybe make some changes to the under relaxation factors to see if we can get it to converge better if necessary. So let's plot the residuals. So as predicted, our residuals have kind of reached a point and stopped converging further, stopped reducing further. Not only have they done that, they've also reached a point where there's very clear pattern to their oscillation. Now, that is a strong indication of transient behavior. So once again, trying to solve a transient flow field in a steady state case will result in behaviors like this. So as we said before, there's a few things we can do. The first and most easiest to do is to change these under relaxation factors. So our pseudo transient under relaxation factor, use a smaller timescale factor to try and damp out these oscillations. And also in our under relaxation factors for our pressure, momentum, and density. Density, we're having a constant density, but we can change this pressure under relaxation to maybe 0.2, momentum to 0.2. So pressure, obviously, so what we're looking at, momentum's not too bad. Our X, Y, and Z are pretty low, so maybe we could leave momentum. Pressure is our continuity. That's really struggling, so it's unable to converge past below e to the -2. You can see here continuity, x velocity, y velocity. And our turbulent kinetic energy is also struggling, so maybe we'll put that to 0.5. Okay, so our residuals are oscillating, and so are our quantities of interest. So if we were looking to here, we'd look at our max. Between our max and min, there's only a difference of about 2 newtons, well, not even 2 newtons, 1 newton in a 3,000 newton solution. Maybe that's not such a big deal, Drag values, we're looking at a difference of about 0.5 on a potential on a 13.5 newtons, so a bit more than 0.5. So we'll call it a newton on this one as well. So that's a bit higher of a percentage, so maybe less tolerable. And our standard deviation, that indicates to me that we're really not, we don't have a big enough flow field. So we don't have a big enough enclosure. So our outlet is too close to the body of interest and is still being largely affected by what's happening at the body of interest. Okay, so if this was my model, I'd probably take this away. I'd make the domain bigger. That would help convergence behavior likely as well. And then I'd change those under relaxation factors, which we've done, and run again. And let's see if changing those under relaxation factors changes this convergence behavior that we're seeing here. And we'll come back to this model. Okay, so SBES, stress blended eddy simulation. How do you create the downforce, drag, and outlet SD? We've been through that. So if you go back through the video, you'll see it, but it's just in here. So definitions, specify a definition for a force or for a standard deviation or a pressure value, vertex average, vertex minimum, volume average, things like that. Okay, so for those of you who haven't seen, this is Workbench. Workbench is an Ansys tool that is a really great way of collating data. So all of your different simulations, in terms of all of the different licenses that you have access to, so structural simulations, thermal simulations, fluid flow in both Fluent and CFX, Polyflow, you can drag any of those onto here and use those systems. You can basically connect between systems. So if we wanted to do a one-way fluid structure interaction, we could bring a structural case on and share the solution to that setup. And that would provide a way of putting the pressure contours, pressure plots onto a static structural model and solve the FEA based on the pressures calculated in the CFD. Another thing we might do if we wanted to have a two-way fluid structure interaction. So that's a one-way. So we solve the fluid field and we put it onto the structure, but there's no feedback between the two. If there's feedback between the two, if it's two-way coupled, we can do a system coupling and we can feed them both into system coupling there. And basically the fluid flow will change, we'll put pressure on the structure will deflect, those deflections will come back into system coupling, back out to fluid flow, the mesh will update, and back and forth. And it's a back and forth process. And all of that's made really easy by what's called Workbench. So if you have it installed, all you have to do is type Workbench, get the latest model up. So this one, we've got a Fluent model, which I don't have open. So I'll double click on solution here because we want to bring the data with it. And I'll show you the setup of this model and the reason we did it. This isn't the actual model of the client. This is a simplified model that I set up for them just to show them the setup. But it was a very similar geometry. So we can see here, note, the current turbulence model should only be used with bounded second order implicit transient formulation. So any of those large eddy simulation models, those middle range models that allow us to pick up larger turbulent structures, need a higher order transient formulation. So the specification should be second order at least. And you can see that will be in here. So that should be bounded second order implicit. Okay, so this is the model. We've essentially just got an inlet here, converges down to these channels, and then the flow is just allowed to go out into atmosphere. So this is essentially atmosphere. And what this is representative of is a sleep apnea mask. So someone will be sleeping, they'll have this mask on, and it's a mask that is built to kind of monitor their sleeping patterns. And because of that, the person's supposed to be asleep. We don't want the air that they're blowing out through these holes to be making too much noise. How do we understand noise in a flow field? Well, we really need to be picking up turbulent structures. We need to be picking up pressure oscillations. Okay, and a RANS model won't necessarily be able to do that for us. So we want to be able to turn on our stress blended eddy dissipation and solve the turbulent structures in a transient sense. So the transient model will solve time step by time step and allow us to pick up the turbulent structures. So first we're going to go through it all. We check our mesh. There's 4.5 million cells. Lucky we don't have to solve this one today. And our quality is 0.16. So that's a good quality mesh. And the other thing that's really specific to this mesh is the sizings and the locations of the sizing. So you can see that we've got quite a coarse grid here and quite a fine grid in here. And that is because we want to only use the stress blended eddy simulation, the LES model, in this region here where we're expecting the turbulent flow. We're not expecting much turbulent here when there's flow just converging down to these points. The flow as it comes out of here, there'll be a jet stream here, and this flow is stationary. That's where we're expecting to see the turbulence. Okay, so we have much finer grid in here. And you can see this time we've used a tetrahedral grid. And yeah, so at the walls, we should see RANS model being used, and in here, we should see the LES model being used. And we don't want to be picking up LES model near the walls because remember, like I said, at the walls, the turbulent structures are really, really small, and SBES allows us to use large eddy simulation with less mesh elements for cases like this. Okay, so in general, we're using a transient model this time, not a steady state. And we are, in this turbulence model, having our K omega SST at the walls, but our SBES hybrid model turned on. Okay, so we've got our stress blended eddy simulation turned on, and that's basically all you have to do to specify SBES. Got some pretty simple boundary conditions otherwise, just an inlet velocity of 15 meters per second. Outlet is pressure outlet. And the rest are just walls. So otherwise, a very simple model other than having a higher order turbulence model on. This should be a second order implicit because we need that to resolve the turbulent structures in time better. And we're using a simple scheme, so a segregated solver this time. These were all defaults. The definitions that we used were, we don't have any created in this model specifically. One thing that we did do is to solve the model first with RANS. Okay, So one thing that you do when you're doing a transient model is you want to get a really good, if possible, you want to get a really good steady state solution first, because that's a really good starting point. So remember, when we do our initialization for a steady state solution, we want to have a really good, we can have an even better initialization for our transient solution by getting a steady state solution first. So we solve our RANS model, our K omega SST, and it'll give us a result like this before we turn on our turbulence and then turn on our time stepping. So you can see here we've got quite a small time step size. This will be selected based on our convergence. So we can pick a small time step, and if it's not converging, pick a smaller time step. If it is converging, really easy, pick as large a time step as we can until it stops converging really easily. Okay, so this is our starting point for our transient first time step, but let's have a look at what it looks like once it's solved. We've taken a couple of animations out and when we solved it last time. You can see we're going through the frames here. We've got 500 frames to get through. Just seeing here now the flow start to break up a little bit and become turbulent. So there's been a transition. The flow has become turbulent, and we're picking up those turbulent structures in our SBES model. So we won't necessarily pick up that kind of oscillation if we're just using a RANS model alone. And it's really important for us to pick up this oscillation because a lot of the sound that we have found to be problematic for the clients using the sleep apnea mask is coming from aeroacoustic effects. So in order to get aeroacoustics, we need to be using higher order turbulence models. That's the moral of the story here. Now, the way in which we can understand the actual aeroacoustics is to put a point or a few points in the flow field here, because now that you can see we have an oscillating flow field based on the jet coming in and the shear stress between the shears between the jet and the stationary flow, we can have multiple points in the flow field here that will tell us what the oscillating pressure value is at those points. So the static pressure at each point will give us show us what the oscillation in static pressure is with time at each of those points. Okay, and that'll come out much like these plots here. So you can see that these plots here are drag per iteration. These plots will come out as pressure as a function of time, because each iteration or each time step in here is advancing in flow time. And what we can do with that information is Fluent already has built in it some handy tools to do fast Fourier transforms. Okay, so these Fourier transforms can be used to take pressure versus time plots and turn them into decibels versus frequency. Okay, so we can actually pick out what frequencies are active in those aeroacoustics and what decibel level they'll be at based on those pressure values. So that's a bit more of an advanced model. Like I said, we did for a client on support. Does anyone have any questions on that model before we move forward? There's a few questions here. If you know that your system is transient, but you perform a steady state simulation for initial conditions, can you be more forgiving of your steady state results? More forgiving? I think it's still really important to be getting as much of a converged steady state solution as possible. So I'd probably be likely to be as as rigorous in my assessment of how well the first initial steady state has converged, because your starting point for your transient simulation can completely change where your transient simulation ends up. Okay, so your starting point is really important to get right. So I wouldn't say you can be more forgiving necessarily. Shubhashish, for most of the practical cases, turbulence parameters at the inlet and outlet boundaries are not known. Does Fluent have any recommendations apart from the default values? Once again, that's case specific. I'm not sure what the Fluent recommendations are per se. You can maybe read through the theory guide. There will be some information, some helpful information in there. A lot of it is based on prior research. So if you're doing a case, a uni project, often there will be some papers on there. They'll have justification for the turbulence parameters that they've used. So often you can go based on that. Also, like I said, in the case that I built with an ABL, an atmospheric boundary layer, there is specifications in the standards that tell you what turbulence intensity should be seen at each level, and level being the distance from the ground plane. So there, yeah, there. I mean, a wind tunnel, we know that the turbulent intensity should be around 1% or lower. So yeah, it's case specific, and there's not necessarily going to be easy answers for it. I would be looking at research. If you can't find it in the help files, going towards research and other people's simulations before moving forward. Can you comment on the computational power or RAM required for these kinds of simulations versus the RANS static simulation used to initialize it? The RAM is more of a function of the number of elements in the system. So it doesn't necessarily require more RAM to run a transient case as opposed to a steady case, but it usually requires a lot more iterations. So where we can get a steady state case to converge in, say, 500 or 200 iterations, a transient case needs to converge every time step for thousands of time steps, and each convergence for the time step will require around, for a good transient case, 3 to 5 iterations per time step. So your time spent is going to be longer because you need to solve more iterations, but your RAM usage and your power is more based on the actual number of elements in the domain. How do you handle a varying transient solution when you're doing a mesh independent study? Great question. Difficult one to answer. I'd be looking at trying to get a steady state case that could be assessed for convergence before turning on transients, rather than using a transient simulation for doing a mesh independent study, if that's possible. Ideally, if for this case, you'd have some kind of value of maybe velocity at each point, something that you can measure that's more static, that can be assessed as being static, and then doing a mesh independent study of that. Also, the mesh independent study is more of a comparison between multiple simulations rather than comparison between simulation and real life. So my mesh independent study for this might be trying to get maybe your standard deviation at the outlet and changing your mesh densities until that kind of outlet quantity stops changing. But our mesh independence for things like our SBES, where we need to have a really high mesh density to pick up some of those turbulent structures, these need to be calculated based on with the LES model. Like I said, when we get our large eddy simulation model, what we're trying to pick up is the highest energy usage of turbulent structures. So there's a turbulent structure size that is is consuming the most turbulent energy. So our mesh size should be based on what that size of that turbulent structure is. So some function of that, rather than our mesh independent study in the traditional sense. For the residual plot, is 1e to the 3 enough for accuracy? Is there any point in trying to go further? Yes, there is. Depending, it's very case specific. Once again, I've had cases where my monitor points were still varying and the residuals had reached 1e to the negative 3. So if you ever get that where your monitor points, these ones are still varying, but your residuals have dropped below 1e to the negative 3, then I would change my residual convergence parameters to be lower in order to get the monitor points to stop changing with iterations. Okay, so we've got a question about current numbers. Can we explain more about the CFL number in Fluent? 200 seems really high. So, okay, so what the current number is, for those of us who don't understand, is it's based on the time it takes the fluid flow to get from one side of a mesh element to the other. Okay, so a current number of 1 would mean that our flow won't go any more than one mesh element across in one time step. Okay, because if our time step's quite large, we're solving the flow at this point, then we're solving the flow at this point, it's jumped all these elements. So our current number is a way of assessing whether our time step is correct for having a for having a good resolution in space. 200 does seem really high, and it is just a default to use when you are setting up your simulations. You can reduce that quite drastically, but for some steady state solutions, 200 can be fine, very case specific. When we're doing transient simulations, it can be more important to have low current numbers, and those can be assessed after doing the simulation and then maybe changing the time step. And once again, a lot of these things are very case specific and require a bit of trial and error. Okay, so that's the turbulence model. We're going to go into a little bit of modeling the boundary layer, and I think that'll probably finish us off for the day. Just get the slides up. Here we go. Okay, so you've heard us mention inflation layers, boundary layer quite a lot. And the reason is because it's a really key component to getting an accurate CFD simulation. And it's also really difficult to get a really accurate CFD simulation. So really difficult to get an accurate understanding of what's happening in the boundary layer. And that is because what's happening in the boundary layer is usually happening at quite small time scales and quite small length scales. Okay, so our boundary layer, we'll go from the basics. The boundary layer is when we have flow going over a surface. At the surface, the flow is 0. Okay, and it's increasing velocity with increasing distance from the surface until we get to free stream. Once we get to free stream, we're no longer in the boundary layer. Now, our boundary layer consists of 3 distinct regions. Our viscous sublayer, right down the bottom, really close to the wall. Our log layer in the middle, or our transition layer, and then an outer layer. Sorry, there's another layer in here. Viscous sublayer, transition, and the log layer are usually the main layers that we consider for simulation. The outer layer is getting more towards being in the free stream. So you can see here that our velocity profile, velocity will increase with increasing distance from the wall. Now, these are the three layers that we were talking about before. So we get our viscous sublayer, our buffer layer, and our log law region. And we're introducing this value called our Y+. So our Y+ is much like Reynolds number. It's a non-dimensional number. It's a function of our position in the boundary layer, which is actually calculated as a function of the Reynolds number. Okay, so our position in the boundary layer can be represented by a value called our Y+. And you can see here that our viscous sublayer is a Y+ value of between 0 and about 5. Our buffer layer is between 5 and about 30. And our log law layer is 30 to about 500. In here it's 100, 200, but goes up to about 300, 3 to 500. Okay, this is really important because of this. So there's different things happening at the different layers. The viscous sublayer, sometimes called the laminar sublayer, which gives you an indication of what's happening. It's usually quite laminar flow. Our transition layer is the transition between the viscous and the log law layer. That is usually highly transient, not highly transient, sorry, highly turbulent. And then our log law layer is the region within which the velocity is increasing with the log of the distance of the wall. So three quite distinct regions and need to be picked up in order to get an accurate understanding of adverse pressure gradients and behavior near the wall. In the near wall region, the gradients are high, but accurate calculations in the near wall region are paramount to the success of the simulation. So the two ways to model the near wall region is either using wall functions or resolving the viscous sublayer. This is both with using the K omega model or the K epsilon models. So using wall functions, we're allowing the functions inbuilt into the turbulence model to do the assumptions and the calculations for us. So you can see here that we've got only a couple of boundary layers, inflation layers in the boundary layer. Whereas if we resolve the viscous sublayer, we've got a lot more inflation layers. Okay, so this one is seen to be more accurate. Now, the important thing with both of these is getting the Y+ value right. Okay, so Y1 is our first layer height. The first layer is, our first inflation layer. So this is our Y1 height. It's important to understand where that is in the critical regions. So the critical region would be on the front wing in the other case where it's likely to separate, or just before. We need to know what Y+ value that is, because when we're using the near wall model, using the wall function, typically we need to have a Y+ value of 30. Okay, so we can have our first layer height in as a Y+ of 30, and our model, our K omega SST model, has an assumption about what's happening in the viscous sublayer. Okay, it's a well-validated model. It requires less mesh elements and can be really useful for reducing the mesh density in your simulation. Now, if we resolve it fully, we need to go into the viscous sublayer, which means we need to have a Y+ value, a Y1 of Y1 height in about Y+ equals 1. Okay, and our mesh, prism layer mesh, should not have a higher growth rate than 1.2. So that's how much thicker the layers are getting with increasing distance from the wall. Once again, these are not magic numbers. This guideline ensures that the mesh will be able to adequately resolve the gradients in the sublayer, but always rely on a mesh independent study or assessment of your results. Okay. So one of the ways we might assess our results is through looking at something that's called the turbulent viscosity. Okay, so now in this case, we've got three different cases. What we're looking at a turbulent, we're looking at velocity. No, this is the vectors of velocity, but the contour in the background is turbulent viscosity. Okay, And the reason that's critical and important is because it shows us what level of the boundary layer we're in. So you can see here that 15 layers goes up to here, 20 layers up to here, 25 layers, and 30 layers up to here. They're all starting from a very low Y1 though. Okay, so it looks like all of them were resolving the viscous sublayer. So if we're trying to resolve the viscous sublayer, we need a Y plus of 1 at the first layer height. And we can tell what position in the boundary layer we are by looking at this plot. And you can see, if I go back to the other plot, our three distinct regions, our viscous sublayer, our buffer layer, and our log law layer. The buffer layer is more transient, not transient, I've done it again, more turbulent. Okay, so there's a higher level of turbulence. So our turbulent viscosity should be increased. You can see here that in all of the simulations, we start a low turbulent viscosity, gets higher and goes back to low. So we know this is in the buffer region. This is in the log law region. So for us to assess whether or not we've got enough inflation layers to have picked up our boundary layer, we're looking at the viscosity plot to say, okay, I can see that we've gone to higher turbulence and then back out to lower turbulence viscosity. And I would say that this has not picked up our boundary layer very well. A little better still. Probably need 30 layers if we're going to be resolving the viscous sublayer to a Y plus of 1 and still having enough mesh elements to capture all the gradients in the boundary layer. Okay, really important to get it right, especially for external aerodynamics cases like that of the vehicle, the SAE vehicle. And remember, we can also resolve the viscous, we can also not resolve the viscous sublayer and use wall functions and maybe have our first layer height closer to the buffer layer where we're at about 30, a Y plus of 30, which might be around here, but you'd still want about 8 to 10 elements total in your boundary layer to make sure you're still capturing the gradients from 30 all the way up to 300, 500 Y plus values. Is Fluent better than Hypermesh? I would say yes. I'm paid to say yes, but I'd also say yes because I think it is better. Any other questions before I move on? I'm going to move on to some, maybe we'll check the solution on the other one. I think that's gone far enough. Okay, so that's our near wall modeling. If you have any questions about near wall modeling, let me know. But it's suffice to say that getting our boundary layers, our inflation layers in the boundary layer, having a correct number of inflation layers and understanding what level of Y plus we're in for our first layer height is really important. Okay, so now we've gone through, remember what we changed? We changed the timescale factor to 0.1. So that's our under relaxation of our pseudo transients. And we changed our under relaxation factors of pressure to see if we could get a better convergence on this continuity plot. I had a couple of questions come through. How inaccurate would be the calculation if finer mesh Y plus of 1 is used along with wall function? The wall function is an automatic specification. So when we turn on our K omega SST, it basically assesses what level of the boundary layer you've started in, and then uses either the wall function or a resolution of the viscous sublayer to suit. So you can't do both. In regions where the first layer height is in around a Y plus of 30, it's going to use a wall model. In regions where you've actually resolved the Y plus of 1, it's going to use the full resolution. So I sort of asked this, but I appreciate further clarification. For validation to select the most appropriate turbulence models, would you recommend using 2 different near wall mesh resolutions? Okay, so in this case, a y plus of 1, if you're tossing up going between a y plus of 1 and a y plus of 30, in terms of using it for validation case, if that's ever a question, if you have enough computation power to resolve to a y plus of 1, then resolve to a y plus of 1. If you only have enough computation power to resolve to a y plus of 30, because the difference in the amount of elements in the domain can be very significant for those 2 different values. If you can go to y plus of 1, that is preferred. So if you can compare k omega SST to a k epsilon with a enhanced wall function for a y plus of 1, then do that comparison. But like I said, the validation and the ability to select an appropriate turbulence model is based on prior research. It's based on other people's models that they've built in the past. It's based on what, models that your research group is using and why, not just, an understanding of the theory. Okay, it takes a lot of research before selecting a turbulence model and being sure of that selection. What is the relation of inflation and wall function? So inflation is just referring to these layers in the boundary layer here. And what it means is, the reason it's called inflation is because you can see that at the surface, it's, follows the contour of the surface, and then you're stepping out from there. So you're inflating each mesh inflation layer from that starting point. So these are just inflation layers, and they're just a mesh strategy that allows you to get mesh elements that are aligned with the flow direction close to the wall. And that's just the best way that we've found of resolving boundary layers when using RANS models. Okay, let's have a look at this. So we've got about 20 minutes. Okay, so let's go through some post-processing. Let's finish off this, this model that we've solved. So we can see that we've got very different convergence behavior when we've changed the under relaxation factors. So that transience that we had seen has been kind of damped out, but we're not quite resolved to a converged solution yet. If this was a model that I was using for assessment of an aerodynamic vehicle, I'd probably run it for another few thousand iterations before I really post-processed it, just because I'd say it looks like maybe this stuff would, we'd either go into another oscillating regime, or this would then be able to converge. But you can see here that based on the changing of the under relaxation factors, the monitor point of lift has become, downforce has become more stable. Drag kind of became more stable, and then has gone along with this, the rest of the solution, to be in an unstable state. And the standard deviation is stabilized a little bit, but like I said, I would be running this for a lot longer. And maybe even reducing, if this drag and these residuals continued to be oscillatory or unstable, or neutrally stable, essentially, with the oscillations, I would change the under relaxation factors and maybe reduce them further before simulating more iterations. But imagining that we do have a converged solution, let's look at some ways in which that we can post-process. So one of the main ways that we would post-process for a vehicle like this is we want to know the pressure contours on the body. I'll just get rid of the ground. Okay, so we can see where the highest pressure is and where the lowest pressure is. So you can see that we've got nice high pressure on top of the wing, pushing the wing down. We've got a nice low pressure on the bottom of the wing, pulling the wing towards the ground. So there's going to be a good amount of force being generated. You can see that we've got quite a high pressure region in front of this front wheel. The front wing hasn't done a great job of moving the air away from the front of the front wheel. And anybody who's done any aerodynamics design for a vehicle like this, any formula vehicle, the most difficult thing to design around is the open wheels. They'll always produce lift, and they'll always produce a lot more drag than other components because they're exposed. One thing I like to do with the pressure contour when assessing external aerodynamics of a vehicle like this is to change the plot to basically put zero pressure in the middle, so you can see more clearly what is actually sucking and what is actually pushing. So because you'll see, if you can see here, that our 0 point's actually up here, and we're getting a lot lower pressures, gauge pressures, static pressures, than we are higher pressures. So one thing we can do is we can edit this, make it split. And we want to know our maximum and minimum, just so we can get a ratio. Maximum pressure is 90. You can see that in here. I might not use the global range though. Yep, still 90. And the minimum is -491. So I just want to know where the 0 point is. It's about 15% from the top. So this white one will go to 85. And then we'll put dark. Sorry, get there in a sec. There we go. Apply that. Close, close. So I like using this view because, like I said, you can really clearly see the regions that are sucking and the regions that are pushing. So anywhere there's green, it's a high pressure, it's above gauge pressure. Anywhere where it's blue, it's a low pressure, it's below gauge pressure. So you can see that, you know, there's a lot of low pressure on top of the chassis. Not a good thing because it's going to be producing lift. Quite a high pressure underneath here. So we can validate our assessment of that, obviously, by going through our forces. Take ground off, -1. So you can see here, the overall, we're getting about 3 kilonewtons of downforce. That's good, 3.4. No, okay, so what we're looking at now, we've got actually quite a lot of lift being produced by our front wheel. Okay, so we've actually got more lift being produced by this vehicle design than we are downforce from the front wing. The front wing's got quite a lot of, a small amount of downforce from this high pressure, low pressure differential, but our front wheel, due to the fact we haven't been able to divert the flow well enough, a lot of high pressure underneath and low pressure on top, is showing a lot of lifts. There's a lot of redesign to be done to a component like this in order to get it to be performing in the way that we'd want it to be on a vehicle. Can we set up a turbulent kinetic energy plot to assess if the inflation layer is capturing the boundary layer? Yes, we can. I'll show you exactly how to do that. So one place we might do that is on this front wing. So we look at the bottom layer of the front wing. Just see where this plane is. Yep, that's where we want it. So what we want to do, if we remember, in our understanding of our capturing the boundary layer through inflation layers, we want to see a plot that can show that we have enough inflation layer elements. And one of the ways that we could do that is looking at the turbulent viscosity ratio. Okay, so put that on plane 9, and we're going to save and display. Okay, so there's going to be a lot of turbulence in regions outside here, so we often need to change the range. There we go. So we can now see that we're getting a turbulent viscosity that goes from low to a higher value and back to low again. So that's more easily visualized here. So we've got a low value to a higher value, then back to low again. So if I make this 80. And what we can see is that we're not really going low and then high. So what we should do is, oops, plane 9, all edges, no faces, save and display. I'm going to change that color to black, should be fine. And then we're going to show this plot over the top. Okay, so this was just an example mesh. Obviously, this is not what we would want to see a mesh looking like, an inflation layer looking like. So really, if we were to be picking up what's happening right down the bottom here, we'd probably see a nice dark blue layer into a green layer and then back out to blue. And that's to show that we're picking up the laminar sublayer or the viscous sublayer, the buffer layer, which has a higher turbulent viscosity, and then into the outer layer, which should have a lower turbulent viscosity again. I think you might be right about the wheel specification there, Roman. We can do some streamlines for this model, definitely. I might do a vector plot on this one just to show how we do that. One of the things we need to be doing here is showing how we're doing things as well, how to do all the different post-processing techniques. So if we do a vector plot, we can do that on a plane. We can use that to see the point at which the flow is separating. So you can see here between these two elements, the flow has started to separate, it's turning around. And a lot of high. Okay. So we can see here that we've done the wrong rotation velocity, the rotation direction for the wheel. So the wheel should be rotating forwards and the flow at the surface of the wheel is going backwards. Is that correct? Let's put vectors on the wheel. It's not really a clear rotation, is there? Let's check out boundary conditions for the wall. I think it's definitely not rotating at the right speed, if anything, because it should be very clearly going this way. And the velocity at the surface should match that. So there's something I need to check. Maybe we'll check that for tomorrow, but it's good for us to be able to see this and figure out and show how to troubleshoot a simulation like this. Can you visualize Y plus? Angus, yes, you can, only at the surface though. So one thing you can do is to go, it's a good idea to show that. We'll just do a Y plus plot on the front wing. So you can see that we're looking at 153 Y plus in the region that's probably critical to have a really low Y plus, because in this region is where it's going to start to separate between here and the wing flap. In here, we've got quite high Y pluses as well. Yeah, the input magnitude for the rotational velocity. It's 11.1 meters per second. And the wheel's radius is 0.228 meters. This is definitely something that's going to require a bit more investigation before tomorrow. Rotation direction is X. Thumb out, wheel should be rotating forwards like that. Okay. All right, what else can we show quickly before we end the session today, even though the model might not necessarily be 100% correct? So Stefano, good question. I assume because we saw the inflation layer not capturing the boundary layer with enough elements that this could be causing residuals not decreasing smoothly. This is an annoying thing about CFD. That's not necessarily correct. So not resolving the domain with enough elements is not necessarily a problem for convergence behavior, because if you're not resolving with enough elements, it's actually an easier solution. So if you think about it, say hypothetically, let's look at this from this way. If you've got there we go. If we've got flow coming in, hitting the front wing, the high pressure is pushing the flow off this way and the low pressure is sucking the flow around this way. Okay, so we're going to have a rotational vortice coming off the front wing. Now that's a really easy way to visualize it, but that's going to be happening in a bunch of different locations. Okay, so there's quite small vortices coming off everywhere. So there might be a main vortice coming off this flat, but there might be smaller vortices coming off as well. So the more mesh elements we have, the more flow features we're going to be picking up. And those flow features can actually be exposing the solution to more transients. So this kind of convergence behavior is not necessarily a function of your mesh size. Your mesh size is going to give you a greater, a smaller mesh size and a higher mesh density is going to give you more accuracy, but it also can contribute to more transient phenomena being picked up. But it could be that these values, which seem quite wrong to me at the moment, usually the front wing will be producing the highest magnitude of force. That might be due to a lack of accuracy in our simulation at the moment. Yeah, some more things that we can do to assess convergence from Jonathan. One thing we might be able to do is to look at residuals. So we can, I'll plot it on the contour on a surface first. You can see we can plot residuals. So it just gives us mass imbalance, but if we turn on expert options, we can get more options. So we can see quite high mass imbalance in the wake region. And one thing we can do, which we might show something quite important for us to understand is if we turn on edges, it's not very good color, but for now it should do. Oftentimes we'll see this kind of high mass imbalance, high residuals around the regions of that 1 to 8 octree transition. So remember when we talked about the hex core mesh, so having a cubic mesh in the bulk fluid region is good for increasing convergence speed. So it's a more efficient way of solving the solution, but it can introduce problems in this 1 to 8 octree transition. So one of these cubes is actually 1/8 to the volume of one of these. Now that transition can be negative for convergence behavior and residual mass imbalance. So there are some methods. I'm not sure if Hashan showed you yesterday when generating a polyhex core mesh, you can put in buffer layers. And there's essentially like this. So it goes from these inflation layers to a polyhedral to a hex core. So in between the layers of hex core, there'll be a couple of layers of polyhedral and then into more hex core. And that can be a really good way of having the benefits of a hex core without this 1 to 8 octree transition. And so, yeah, so that's going to be caused by maybe not having a small enough mesh or a constant enough mesh in the wake region behind the vehicle here. And that can be helpful if I was to do, we can do another thing which is called a isosurface. These can be really helpful. We'll do it of residuals, compute. All right, let's create that one, close, and then we'll go mesh. We'll use that mass imbalance. Actually, we'll do a contour on it. So mass imbalance, and we'll color it by pressure, or we can color it by turbulent kinetic energy. Save and display. So everywhere within these isosurfaces is a high residual at the moment. So we can add this to graphics. No, we don't want that one. We want that pressure one. There we go. All right, so we can see we've got big problems here and here in terms of our residuals. And we could assess that as being maybe a mesh problem or being a just a problem. Maybe it's a transience thing. Maybe that's where the wake is the most chaotic. And it may be that we want to reduce our mesh size in those areas. What else? Is there anything else? There's some plots and things we can do in here. Often they'll come out like this. We can generate lines to plot different things on. I can take us through some more post-processing tomorrow. But I think for now we'll end it. Will I touch on multi-phase modeling at all tomorrow? I can do. I'll see if I've got a model already built and solved that we can go through. I'm not sure if it's in the notes here already, but I can discuss something. I can discuss some of that tomorrow, yes, as well. Okay, so we'll call it a day there. Come back at 9 a.m. tomorrow. Is there any other questions before we go? Remember, have a go at some of these tutorials. We can talk here till we're blue in the face, but doing some actual solutions, solving some models yourself, going through this training material is really is a better way of getting a good understanding of what's going on. Okay, thanks guys. Speak to you tomorrow.